So, good morning, all of you. I hope people have joined online also. Right? I will start. So, as promised, I am going to talk on Laplace equation. I already mentioned, and it was already mentioned in the previous lectures also, that Laplace equation corresponds to the stationary state, both in the hyperbolic case, that is wave equation, and parabolic case, that is the heat equation. So many times, so the equation which I'm going to write, most of the things I have followed from Evans, and you all can use that as a reference. So I will try to say something more and be sketchy. For details, you all can refer or try to work things out. As I had mentioned yesterday evening and even during Harsha sir's lecture, most of the time what you are using is integration by parts. Whatever calculus you are learning at your undergraduate level, in fact you end up using now. For the proofs are usually not very difficult. The interpretation and the outcome of the proof is very heavy, like it is very good. You can read of many things even without solving the differential equation. Okay. So for u belong to C2 of u subset of R3 or Rn. So I always tell the students that if you want to understand something, then or even students or anyone, that if you want to understand anything, you should try to work it out for 2 dimension and 3 dimension, because you are at least able to visualize what we are looking for. Okay, you don't get scared by the number of variables, just Rn. No point doing everything for Rn. There is echo, no? Okay. So this is called as Laplace equation. Your Laplace operator is so this is same as d square by dx square in n equal to 1, d square by dx square plus d square by dy square in n equal to 2. Okay. And there is so here you are having 0 on the right hand side. If I have function f, so this f may be f of u, f of x u, depending on x also and u also, all the cases. Okay, so this is you refer to as Poisson's equation. Okay. So we are not concerned with regularity over here. We are just assuming the function is C2. We want to differentiate it 2 times, and that is what we are thinking about. So coming back to this particular equation, we have already seen, the students have already seen this equation in complex analysis, right? You have already seen this delta operator in complex analysis. If u satisfies Laplacian u equal to 0, you say that u is a harmonic function, right? So okay. So this is I do want to take the opportunity to relate this concept of harmonic function to what you have studied in complex analysis. So of course we don't want to work in complex space. So if you remember, a function is complex differentiable if So complex function is written as u plus iv, and then you have Cauchy-Riemann equation, and then you also end up proving that u is harmonic, v is also harmonic, right? So if you have one u, real part of the complex valued function, real part of complex valued function which is differentiable is going to be harmonic, and then you have methods to using Cauchy-Riemann equation, you find out the what we call harmonic conjugate, right? So you find out, given u, you can find out v, given v, you can find out u. So of course, one of the things is you don't want to work in complex space, right? So we are interested only in the real function, and you are just going to study this equation, Laplace u equal to 0, and this function is going to be harmonic. What we will see is how much similarity it has to complex differentiable function. Lot of properties which we study for complex functions, complex differentiable functions, we will see that in fact they hold true even for a function u which is harmonic. Okay, so it is still nice, right? You are no longer working in complex space, but you still have, or you are still able to extract some of those beautiful properties. So let me ask, you all remember some of the properties of analytic functions? Analytic functions, what are the properties of analytic functions? Do you all remember? This requires only basic complex analysis course. So what was the, which are the properties of complex functions, analytic functions that you remember?
Power series expansion is
Power series expansions. So that's what I'm not going to do it in traditional way, right? So so you have for complex. So let me also write analytic function. So power series expansion, yeah, you had that for every analytic function you have a power series expansion. Then okay, then I want more analysis related properties. Yes. Then
so once analytic, once differentiable, the derivatives also continue to be neighborhood.
yeah. So that is the main difference between analytic function and real function. See, when we say that power series expansion exists for analytic function, you are assuming the coefficients of power series are the derivatives, right? So that is a big difference between C infinity functions and analytic functions. Okay, so there is a difference between functions which are infinitely real valued functions which are infinitely differentiable and analytic function. So it is still not the same. Existence of power series is not the same when you are talking about real valued functions and analytic functions. So what are the other properties of analytic functions that you have studied? Results, theorems. So again related to power series expansion, how did you find the coefficient? Cauchy integral formula, right? You had a Cauchy integral formula. And then what? No, that is too far away. I'm talking about analytics. Residues come for singularities. Yes.
So integral on closed curves is 0.
Yeah, so integral of closed curve. But that is part of this Cauchy integral formula itself, right? So what more did you study? You studied Liouville's theorem. You studied maximum principle. Okay, so you studied maximum principle. You also studied Liouville's theorem follows from maximum principle. So basically, these two I will combine. Okay. So what we'll try to see. So first of all, what does Cauchy integral formula give you? What does Cauchy integral formula give you? So, means I mean vaguely, I'm not asking for the definition. Definition of course one thing, right? What does Cauchy integral formula give you?
Value of the function at a point, given its value around.
Right. So you are able to find out the value of a function. So it's 1/2 pi I integral b x r boundary of bx var. What was it here inside? What was it?
You have used x plus fx.
So here it will be fy. Some So fz something
On the boundary.
dz, right? So it is upon right. So of course that notation is not complex, of course. So you have the Cauchy integral formula gives you the value of the function. In fact, we study later that inside the ball, value at any point inside the ball can be obtained by this particular formula by just knowing the value of the function on the boundary. Okay. So these are some of the properties which we are going to study even for harmonic functions. Okay. So this one is like what similar to, I think even for analytic function you find the mean value property. Okay. This is like mean value property which we are going to show for harmonic function. So if you are having a real valued function, you will still have this kind of mean value property where you can find the value inside the ball in terms of